Welcome back. The next reaction we'll discuss in this chapter is halohydrin formation. So in this reaction, we're adding a bromine or a halogen, like a chlorine, and an OH across the double bond. Okay, that's why it's called halohydrin. So what this reaction is basically a halogenation that's conducted in water. So water is acting as a nucleophile instead of the bromide or chloride ion to open that bromonium ion, that three-membered ring that's formed. So once we form the three-membered ring, then the water, instead of the chlorine or bromine, is acting as a nucleophile to open the ring. So for the overall reaction, we're taking molecule that has a double bond. So for example, one like this. Okay, and we're adding bromine in water. Okay, and so in the first step, we're going to pick up form that bromonium ion by picking up the bromine. Okay, and in the second step, we've got a whole lot of water hanging around. So the water can act as a nucleophile and open the ring, like what's shown here, giving us this intermediate. And in the next step, another water molecule comes along and pulls off that extra hydrogen to give the final product, which is neutral. So we've got a bromine and an OH added across the double bond. What was the double bond? Okay, so what are we adding? We're adding a halogen and an OH across the double bond. So the reason that in this case, the bromide that was kicked out, so remember in the first step here, we've got an induced dipole where we have a partial positive and partial negative on the bromine molecule, and that and then the double bond acts as a nucleophile to pick up one of the bromines and kick the other one out as a bromide. So this bromide is still hanging around here, and it can act as a nucleophile and open the bromonium ion, giving us bromine and bromine added across the double bond. But since we use a high dilution of the bromine in water, there are many, many more water molecules than bromide ions in solution. So the water outcompetes the bromine, making this the major product. So let's look at that mechanism again. All right. Once we form the bromonium ion, water functions as a nucleophile to open the ring. And then we have the protonated species here as an intermediate. So water comes along, pulls off a hydrogen, deprotonating the oxonium ion here to give us the product. Okay, and so we do form a pair of enantiomers because the bromine could be, going down, the OH going up, and so forth. Okay, so if we have, so this is called a halohydrin as a product. And here we have a chlorine in the presence of water, and this is called a chlorohydrin. Okay, so we also have regioselectivity here. The halide is going to add to the less substituted carbon, and the OH is going to go to the more substituted carbon. And the reason that happens is because if we have an asymmetrically substituted alkene, in the first step, that alkene is going to attack the bromine of the Br2, forming that bridged bromonium ion species, because then one of the pairs of electrons from the bromine can form that bridge. Okay, so we've got our bromonium ion here. Now this bromonium ion is going to be, the charge on it won't be symmetrical because we have an asymmetrically substituted alkene, or we had an asymmetrically substituted alkene, and these alkyl groups are going to be electron donating. So as they donate electron density in, they're going to better stabilize that carbocation, placing more carbocationic character on the carbon bearing more substituents. That's going to make the nucleophile add to the more substituted side because it's going to add to the side with more carbocationic character. When it adds to that side, it opens that bromonium ion, opening up the ring, forming the intermediate, which has a positive charge, and now that hydrogen can be pulled off, giving us our product. So we have regiochemistry and stereochemistry to worry about in this reaction. The OH goes to the more substituted side, the halogen goes to the less substituted side, and they add anti to each other. Okay, again, the reason that the OH goes to the more substituted side is because the more substituted side has more cationic character because the electron donating alkyl groups donate electron density in, stabilizing that partial positive charge that's formed better than the less substituted side. So the nucleophile will attack the more substituted side. So let's see if we can predict the major products of these reactions. So for A, we've got, let's just draw the product, the starting material again. All right, and so we're replacing the double bond with what? With, this is Br2 and H2O, with Br and OH, okay? The OH goes to the more substituted side. All right, the bromine goes to the less substituted side, and they're going to add anti to each other, okay? So the OH is going to go to the right side in this case. The bromine is going to go to the left side. And so we need to indicate stereochemistry here somehow. So if the bromine is coming out, okay, then we can put the OH, I'll just draw it like that, on a dash, and put the propyl group on a wedge, okay, and then write plus En. All right, for the next one, we've got methyl. So again, we're adding an OH to the more substituted side and a bromine to the less, and write plus En, and they're anti to each other. So for C, we have this molecule. The OH is going to go to the more substituted side, the bromine to the less, and the carbon bearing the bromine is not a chiral carbon. The other is, so we can write plus En. And then for D, we've got, doesn't matter which one gets which because it's symmetrically substituted. All right, we've got that. And we can say plus En because we get enantiomers. All right, what do you think could happen if we had a different nucleophile here? So for A, let's just write it out. In the first step, we're going to be forming a bromonium ion. So let's just say the bromine goes down here, and we get this bromonium ion, okay? And our nucleophile is ethanol, so let's draw that. So let's think about this mechanism here. Now the ethanol is going to be our nucleophile instead of water. It's going to open that ring. It's going to be more attracted to the more substituted side, which is that side, and then open the ring, okay? So if the methyl group was on a dash, then the OH will be on a wedge, and the bromine will be on a dash. Okay, so we could draw it like that. Not OH, I'm sorry. Ch2, Ch3, right? The ethoxy group. And for the next one, we've got the same molecule, but we need the ethylamine added there in the bromine. So we've got, let's just put that methyl on a dash, the NH, Ch2, Ch3, because remember in that last step we're pulling a hydrogen off, so the nitrogen is going to lose one hydrogen, and then we've got the bromine on a dash, okay, plus En. So we forgot plus En on both of those. Alright, that's our product, and thank you for watching. I'll see you in the next video.